Hello and good afternoon friends, welcome to CEC-UGC live lecture. Dear friends, with another lecture on chemical reactivity and mechanisms. As you know that we are carrying series of lectures on this particular topic, and under this very topic today we are going to discuss about carbenes, nitrines and free radicals. And for this we have again with us in our studios Dr. Vandana. She is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So first of all I would like to welcome our guest Dr. Vandana, and I would like to tell you all that the way she has delivered her previous lectures with the ample of reactions to explain you, to give you deep insight into the topic, I hope that today also she might be having lots of reactions as examples, so that you could be aware of with the carbenes, nitrines and free radicals. So first of all I would like to welcome our guest Dr. Vandana. Dr. Vandana, welcome to the EduSet lecture.
Thank you so much.
So, today we are basically going to learn about carbenes, nitrines and free radicals.
Yes.
So, all is over to you and it is handed over to you. So, please explain us what these terms are.
Thank you so much, Gitika. Hello viewers. In the lecture series of chemical reactivity and mechanism, we will continue the reaction intermediates. We have already discussed in this series carbocations, carbanions. Today we will discuss about the carbenes, nitrines and free radicals. These are also the reaction intermediates formed in a reaction. What are carbenes? It is a neutral divalent species which possess two non-bonding electrons. You can see in the figure that a carbon is having two non-bonding electron attached with the two atom or group. On the divalent carbon is called a carbene. The parent species CH2 is usually called methylene. The derivatives are more often named by the carbene nomenclature. Thus CCl2 we can say it is a dichlorocarbene, though it can also be called dichloromethylene. So we can say both dichlorocarbene or dichloromethylene. Carbenes are highly reactive species, practically all having lifetimes considerably under 1 second. Another example, diphenyl carbene, in which two phenyl group are there. The di-coordinated carbene, carbon of carbene has only 6 electron in its valence shell, 2 in each bond and 2 non-bonding electrons. Structures of singlet and triplet carbenes. Carbene exists in two forms, singlet and triplets. In a singlet carbene, the di-coordinated carbon is in sp2 hybridization state. Two of its 3 sp2 hybrid orbitals form sigma bond with 2 ligands, and the remaining sp2 orbital accommodate 2 spin paired non-bonding electrons. The unhybridized p orbital, which is perpendicular to the molecular plane, remains vacant. You can see in the figure that carbon is sp2 hybridized, and there are 2 sp2 hybridized orbital and 1 vacant p orbital. The unhybridized p orbital, which is perpendicular to the molecular plane, remains vacant. You can see in the figure that this unhybridized p orbital is vacant, while the hybridized sp2 orbitals contains the electrons. The bond angle is about 103 knot, which is less than normal bond angle 120 knot of an sp2 hybridized carbon. Why it is? It is because of greater repulsion force between lone pair and bond pair electrons. Singlet CCl2, Br2C are also bent with bond angles of 100 degree and 114 degree respectively. In triplet carbene, the di-coordinated carbene is in sp hybridization state. You can see in the figure, first figure shows the singlet carbene, second figure shows the triplet carbene. And the hybridization in singlet carbene for carbon is sp. In its sp hybrid orbitals form 2 sigma bonds with 2 ligands, 2 sigma bonds with 2 ligands. The two unhybridized p orbitals which are mutually perpendicular accommodate the two unpaired non-bonding electrons. You can see in the figure unpaired electrons in pz and py orbital, one each in parallel spin. So, the spin of the electrons in triplet state is parallel. So, a triplet carbene is expected to be a linear molecule. In fact, few carbenes are linear. Most are bent with bond angles of about 136 degrees. So, it is a better to consider the carbon is in sp2 hybridization state approximately. The two sigma bonds are formed by two sp2 orbitals. The remaining sp2 orbital and unhybridized p orbital each accommodates one unpaired electron in parallel spin. A triplet carbene is more stable. We will see in coming slide how it is more stable and how much it is stable by singlet than a singlet carbene. The lower stability of singlet carbene is explained by the repulsion between two non-bonding electrons in the same orbital. You can see the relative stability of singlet and triplet carbenes. A triplet carbene is more stable than singlet carbene. Lower stability is explained by the repulsion between two non-bonding electrons in the same orbital. You can see in the figure that in singlet the two electrons is in same orbital. So, the repulsion is minimized and the greater the stability of singlet carbene. The difference between the energy between singlet carbene and triplet carbene, or we can say triplet carbene is more stable by 8 kilocalorie energy. When carbenes are generated by photolytic methods, how can we differentiate that in a particular reaction which kind of carbene is there? Is it singlet carbene or triplet carbene? We can see by the reaction. When carbenes are generated by photolytic method, they are often in highly excited state in singlet state. Addition to double bond is stereospecific. So, how we will then when we add the carbenes in the alkenes, if the singlet species added to cis-2-butene as shown in the figure, the resulting cyclopropane should be the cis isomer. Since the movement of the two electrons, pair of electrons should occur either simultaneously or with one rapidly succeeding other. So, we will react with cis singlet species, then the product will be cis. If attack is by triplet species, the two unpaired electron cannot both go into a new covalent bond because Hund's rule says that they have parallel spins. So, one of the unpaired electrons will form a bond with the electron from the double bond that has the opposite spin. So, a bond can form if the electrons have opposite spin. What will happen then? Leaving two unpaired electrons which will having the same spin, therefore cannot form a bond because they are having the same spin. Bond is only formed when the spin of the electrons are opposite. By the same collision, then what we have to do? Therefore cannot form a bond at once, but must wait until by some collision process one of the electrons can reverse its spin. So, for making a bond, the spin of the electrons must be opposite. It is according to the Hund's rule. During this time, there is a free rotation about the carbon-carbon single bond and a mixture of cis and trans 1,2 dimethyl cyclopropanes should result. You can see in the figure that there is a addition of carbene with same spin, parallel spin, means triplet carbene is added to the double bond. Then there is a formation of intermediate, and after collision the single double bond is reverse and the spin of the electron reverse. Then again there is a formation of trans and cis 1,2 dimethyl cyclopropanes. The result of this type of experiment means that singlet and triplet carbenes when added to the alkene shows that CH2 itself is usually formed as a singlet species. Whenever a carbene is formed, it is singlet which can decay to the triplet state. So, whenever a carbene form in a reaction, it has to be singlet, and after collision it can change into triplet state, which consequently has a lower energy molecular orbital calculations and experimental determinations shows that the difference in the energy, as we have already stated, is 8 to 10 kilocalorie per mole or 33 to 42 kJ per mole. However, it is possible to prepare triplet carbene directly by photosensitized decomposition of diazomethane. We were talking about initially by the photolytic method, how can we create the carbenes. Now, by the photosensitized decomposition of diazomethane. CH2 is so reactive that it generally reacts as the singlet before it has a chance to decay to the triplet state. As to other carbenes, some react as triplets, some reacts as singlets, and others as singlets or triplet depending upon how they are generated. Now, we have discussed the two generation of the carbenes. There is a limitation of use of stereospecificity. We have already discussed about the stereoselectivity and stereospecificity of the carbenes. So, the limitations of stereospecificity of addition of carbenes as the diagnostic test for singlet or triplet carbenes. When carbenes are generated by photolytic method, they are often in a highly excited singlet state. When they add to the double bond, the addition is stereospecific, but the cyclopropane formed carries excess energy, that it is in excited state. It has been shown that under certain condition, what are these conditions? We can say low pressure or in gaseous form, gas phase, the excited cyclopropane may undergo cis-trans isomerization after it is formed. So that triplet carbene may seem to involve, although in reality singlet carbene were present. The most common carbenes are methylene CH2, dichlorocarbene CCl2, but many others have been reported. You can see in the figure that diphenyl carbene and others. Studies of IR spectrum of dichlorocarbene trapped at low temperatures in solid argon indicate that the ground state for this species is the singlet, which we have already proved by the reaction. The geometrical structure of triplet methylene can be investigated by ESR measurement, electron spin resonance measurements. Since triplet species are diradicals, in triplet carbenes there are 2 electrons, but the spin of the electrons are parallel. Such measurements made on the triplet CH2 trapped in matrices at very low temperature. So, only singlet carbene can be investigated by ESR measurement, which is the fundamental concept of the ESR. EPR measurements cannot be made on singlet species, but from the electronic. So, what we have to do for triplet? Electronic spectra of CH2 formed in the flash photolysis of diazomethane, it was concluded that singlet CH2 is bent with an angle of 103 knot. Singlet CCl2 and CBr2, dibromocarbene and dichlorocarbene, which are singlet, are also bent with the bend angles of 100 degree and 114 degree respectively. It has long been known that triplet aryl carbenes are bent. You can see in the figure for the bond angle for the triplet carbene, it is 136 degree, and for singlet methylene it is 103 degree. Generation and fate of the carbene. How can we generate the carbenes? We have discussed about how can we identify the particular carbene is in reaction, is whether it is singlet or triplet. Now we will discuss about the how can carbenes are formed in a particular reaction. The first is in elimination reaction. A carbon loses a group without its electron pair, usually a proton, and then a group with its pair, usually a halide ion. So, in the reaction you can see there is a elimination of first proton and then one chloride ion, and hence formation of carbene. Mode of preparation of singlet and triplet carbenes. You can see the singlet carbenes can be prepared by ionic mechanism, and triplet carbenes can be prepared by photolytic method, diazo compounds. Flash photolysis of CHBr3 tribromomethane produce the intermediate CBr. This is a carbene. The intermediates CF and CCl were generally generated similarly from dibromofluorocarbon and dibromochloromethane respectively. The most common example is the formation of dichlorocarbene by the treatment of chloroform with a base, but many other examples are also known, a few which are. You can see in the reaction that how can carbenes can be generated from different reactants. Another generation, disintegration of the compounds containing certain types of double bond. The two most important ways of forming CH2 are examples of photolysis of ketenes. So, you can see the formation of carbene from the ketenes and from isoelectric decomposition of diazomethane. From diazirenes also give carbenes, because most carbenes are so reactive, it is often difficult to prove that they are actually present in a given reaction. As we have already said that the lifetime of carbene is 1 second. In many instances where a carbene is apparently produced by an elimination or by disintegration of double bond, there is evidence that no free carbene is actually involved. The neutral term carbenoid is used where it is known that a free carbene is not present, or in cases there is doubt, alpha halo organometallic compound R2CXM, R is the alkyl group, X is the haloalkane and M is the metal ion, are often called carbenoids because they readily give a elimination reaction. Other preparations of carbenes you can see in the slide, that there are the examples of formation of carbenes when diazomethane in photolysis when reacts with heat or light, ketones case react with ketones with acid chloride first converted to diazomethyl ketone, it is again photolysis to acyl carbene. Chloroform when reacts with potassium tertiary butoxide in DMSO, dimethyl sulfoxide, there is a formation of dichlorocarbene by the elimination of potassium chloride. NaOH may be used as the base in place of potassium tertiary butoxide. Trichloroacetate ion, when heated it gives dichlorocarbene. N-butyl lithium when reacts with dichloromethylene in presence of hexane, it will give again dichlorocarbene. Phenyl cyclopropane when photolysis gives dichlorocarbene. 2,3-diphenyl oxyrane when photolysis gives phenyl carbene. So, these are the formations of carbenes. These are the examples from which carbenes intermediates are formed or carbenes can be prepared. Reactions. Now, the second part of carbenes, reactions of carbenes. The di-coordinated carbon is in carbenes has only 6 electron in its valence shell. We have already discussed. So, carbenes are electron deficient molecules. For a molecule to be stable molecule, there should be 8 electrons. So, when there are 6 electrons, it is electron deficient. They have a strong tendency to complete the octet of a divalent carbon by acquiring 2 electrons through bond formation. That is why they are highly reactive. Carbenes behaves as electrophiles because of deficiency of electrons. They are extremely reactive and short-lived and never exist as a stable species. Carbenes undergo following types of reaction. Number 1, cycloaddition with alkenes. Carbenes undergo cycloaddition reaction. What is cycloaddition reaction? The addition of carbenes to a reactant and formation of a ring. In the product there is a ring. So, cycloaddition, addition within the formation of a ring, cycloaddition with C double bond C alkenes to form cyclopropane rings. The singlet carbenes undergo suprafacial addition. What is suprafacial addition? Syn addition. in a concerted manner through a three-membered cyclic transition state. The addition is designated as superficial or syn addition because both the sigma bonds are formed on the same surface of the double bond. This is called superficial. The formation of sigma bonds are same on same surface of the double bond. For this reason, singlet methylene on reaction with cis-pent-2-ene produces a racemic mixture of cis-1 plus minus cis-1 ethyl plus minus cis-1 ethyl 2-ethyl cyclopropane, while the trans-pent-2-ene produces plus minus trans-1 ethyl 2-methyl cyclopropane. So, we can say that there is a syn addition or superficial addition. These reactions are stereospecific reactions, reactions in which different stereoisomers of a starting material give different stereoisomers of a product are called stereospecific reactions. You can see in the slide that when cis-pent-2-ene reacts with singlet methylene, there is a transition state which produces the 2 intermediate possibility of 2, and in enantiomer we get plus minus cis 1 ethyl 2 methyl cyclopropane. Another slide which shows the addition of singlet methylene to trans-pent-2-ene. In this case, because there is a syn addition, so product will be trans only, because the reacting material we are taking here the trans and the addition is due to the singlet methylene. So, product will be the same product as that of the reactant, trans 1 ethyl 2 methyl cyclopropane. When cis-pent-2-ene reacts with triplet methylene, you can see the product is 1s2r, it is the stereoisomer, trans 1 ethyl 2 methyl cyclopropane and its isomer, because when triplet methylene is added to the cis-pent-2-ene, then due to parallel spin of the electron, the first electron will form the bond alkene to the first bond, and then there is a rotation about the single double bond, and after spin inversion of the electron there is a possibility of formation of another bond, and we are getting the two product cis as well as trans, as there is a addition of triplet carbene to the cis-pent-2-ene. So, the product here is not only cis but trans also. We are getting here cis 1 ethyl 2 methyl cyclopropane and its enantiomer, and the other product is trans 1 ethyl 2 methyl cyclopropane and its enantiomer. Singlet carbene reacts stereospecifically. We have already discussed that singlet carbene when reacts there is a superficial syn addition. So, there is a concerted mechanism, and when we are taking the cis reactant the product will be cis when it added to the singlet carbene. When we are taking trans reactant and added to the singlet carbene, the product will of course the trans product. So, there is a concerted mechanism, and the mechanism follow the stereoselectivity as well as stereospecifically. In contrast, we have already discussed this in the figure that a triplet carbene is non-stereospecific because it proceeds in a stepwise manner through a diradical intermediate. Therefore, reaction of either of cis or trans with a triplet mixture of plus minus cis and trans 1 ethyl 2 methyl cyclopropanes will be the product, as is in the we have already discussed in this slide. Triplet carbenes react selectively. Two pathways are there. There is a rotation about the single bond, and the product will be the mixture of the isomers, whether we will take cis in reactant or trans reactant. The product will be the mixture of isomers, cis as well as trans. Cycloaddition to carbon-carbon benzene ring and subsequent ring enlargement by rearrangement you can see that there is a formation of carbene, and starting material is, you can count the carbon, there is a 6-membered ring, and after addition of carbene by photolysis there is a ring enlargement and the product is 7-membered ring. What insertion reaction, what is that? Carbenes can undergo insertion into carbon hydrogen bonds. However, we are not observing the insertion reaction with carbenes between carbon and carbon bonds. So keep in mind, there is a insertion of carbenes only in carbon and hydrogen bonds. For example, propane reacts with methylene to give a mixture of N-butane. Hence, the carbon chain is increased by 1 carbon. Means there is an insertion of a group, carbene. You can see the example that propane when reacts with methylene, the product is N-butane and isobutane. Rearrangement, you know what is rearrangement? The atom of a particular group is rearranged to another carbon. Carbenes that have alpha hydrogen can undergo rearrangement to give alkenes as shown in below. It can also form a ring compound. You can see there is a formation of ring and the product is cyclopropane. Acyl carbenes. Acyl carbenes undergo rearrangement to form ketenes which react further as shown below. The rearrangement is known as Wolff rearrangement. Acid first of all reacts with SOCl2 to give acyl chloride, which is then reacts with diazocarbene and further photolysis rearranges to give the product and aldol ketone is formed. This method of conversion of carboxylic acid into its next higher homologue is known as Arndt-Astad synthesis. Reaction with nucleophiles. Carbenes are electrophile, as we are aware of it. There are only 6 electrons. It is electron deficient species, hence electrophiles. So they can react with nucleophiles. For example, reaction of sodium phenoxide with dichlorocarbene proceeds as follows. The reaction is Reimer-Teimer reaction. You can see in the incoming slide that phenol when reacts with chloroform and with sodium hydroxide, you will get the product of 2-hydroxybenzaldehyde. The mechanism is what? The base abstract proton and then there is a elimination of chloride ion, hence dichlorocarbene is the intermediate, and sodium hydroxide when reacts with this you will get sodium phenoxide. It is act as a nucleophile and dichlorocarbene is electrophile, and you can see in the mechanism then there is a substitution by dichlorocarbene, and after the certain mechanism you can see in the slide we will get the product 2-hydroxybenzaldehyde after hydrolysis. This is the famous reaction Reimer-Teimer reaction. Treatment in the liquid phase of a alkane such as pentane with carbene formed from the photolysis of diazomethane gives the 3 possible product in statistical ratio, demonstrating that carbene is displaying no selectivity for many years in liquid phase, but it was a general accepted principle that the lower the selectivity, greater the reactivity. However, this principle is no longer regarded as general because many exceptions have been found. Singlet CH2 generated photolysis of diazomethane is probably the most reactive organic species known, but triplet CH2 methylene is somewhat less reactive and other carbenes are still less reactive. The following series of carbenes of decreasing reactivity has been proposed on the basis of discrimination between insertion and addition reaction. You can see the order: methylene, CH-COOR, phenylene, bromomethylene, with chlorine, alkene, dihalocarbenes generally, which is BrCH double bond ClCH, generally do not give insertion reaction at all. Insertion of carbene into other bonds have also been demonstrated through thou not inserted into C single bond C. Hence, only halocarbenes is not inserted into the C double bond C, single bond C, sorry. Two carbenes that are stable at room temperature have been reported. These are 22 and 23. In the absence of oxygen and moisture, (22) exist as stable crystals with a melting point of 242 to 241 degrees Celsius. Its structure approved by X-ray crystallography, which is in resonance with an halide form with a form containing PC double bond. You can see in the slide tin 23 ka halide plus minus with plus minus with a form containing P double bond C, phosphorus carbon double bond, is a red oil that undergoes internal insertion. The carbenes carbon inserts into one of the carbon hydrogen bonds of an isopropyl group to give when heated to soot. It would seem that dimerization should be an important reaction of carbenes. It would seem, but it is not, because the reactivity is so greater that the carbene species do not have time to find each other, because the dimer generally has so much energy that it dissociates again. Apparent dimerization have been observed. So, actual dimerization is not there. It is due to the energy concern, but it is likely that products in many reported instances of dimerization do not arise from an actual dimerization of two carbenes, but from the attack of a carbene on a molecule of carbene precursor. So, actual dimerization is not found, but actually the carbene attack on the another carbene precursor, as you can see in the reaction. Alkyl carbenes can undergo rearrangement with the migration of alkyl or hydrogen. Indeed, these rearrangements are generally so rapid that addition to multiple bonds and insertion reaction, which are so common for CH2, are seldom encountered with alkyl or dialkyl carbenes. Unlike rearrangement of the species previously encountered, most rearrangement of carbenes directly give stable molecules. You can see some examples of rearrangements. The rearrangement of acyl carbenes to ketenes is called in the last among all the reaction, our last reaction is called the Wolff rearrangement. A few arrangement in which carbenes rearranges to other carbenes are also known. Of course, the new carbene must stabilize itself in one of the ways we have mentioned. Triplet carbenes can abstract hydrogen or other atoms to give free radicals. For your concern, what are free radicals? That have the unpaired electron, a species having unpaired electron. This is not surprising, since triplet carbenes are free radicals, but singlet carbenes can also give this reaction, though in this case only halogen atoms are abstracted, not the hydrogen. So, that is all about the carbenes. Now, we come to the another intermediate, nitrines. What are nitrines? You can see that it is a neutral monovalent species of nitrogen with two pair of non-bonding electron. So, it is called a nitrine. How many types nitrine? We can see alkyl nitrine when R group is there, aryl nitrine when aromatic group is there, and acyl nitrine when RCO group is there. Nitrine are the nitrogen analogous of carbene, and most of what we have said about carbenes also applies to them, to nitrines also. Nitrines are too reactive for isolation under ordinary conditions. Alkyl nitrines have been isolated by trapping in matrices at 4 Kelvin, while aryl nitrines, which are less reactive, can be trapped at 77 Kelvin. The ground state of NH and probably of most nitrines a triplet. Thou nitrines can be generated in both, as same with the carbenes, triplet as well as singlet state. In addition to ethyl COO and to carbonyl double bonds, two species are involved, one of which adds stereospecifically and other not. By the same as we have discussed for the carbenes, how can we identify that whether the nitrine is singlet or triplet, which has been explained by Scales' proposal involving carbene. These are taken to be the singlet and triplet species respectively. Same we can consider for the nitrines. How can we create nitrines? By elimination process. The example is here, the breakdown of certain double bond. The most common method of forming nitrines is photolytic or thermal decomposition of azides. The unsubstituted nitrine has been generated by photolysis or electric discharge through ammonia, through N2H4 or through NH3. You can see in the reaction that there is a generation of nitrines from RN3 and from alkyl nitrine when reacts with alkene. Reactions of nitrines. This is a reaction of nitrines when alkyl nitrine reacts with alkene. There is a formation of aziridine. We will discuss this later. The reactions of nitrines. The reactions of nitrines are also similar to those of carbenes. As in that case, many reactions in which nitrine intermediates are suspected probably do not involve free nitrines. It is often very difficult to obtain proof in any given case that the free nitrine or is not an intermediate. So, it is a difficult task. Insertion reaction is there, nitrine especially acyl nitrines RCO and sulfonyl nitrines can insert into carbon hydrogen bond and certain other bonds. Another reaction, addition to carbon-carbon double bond, and this is the example of addition of alkyl nitrine to alkene, aziridine is formed. Rearrangement reaction, alkyl nitrines do not generally give either of the two preceding reactions because rearrangement is more rapid. Such rearrangement are so rapid that it is usually difficult to exclude the possibility that a free nitrine was never present at all. That is, migration takes place at the same time that nitrine is formed. Next reaction is abstraction. You can see that nitrine can react with alkanes and it can abstract the proton from alkane. Alkyl nitrines do not generally give another reactions of nitrine, Curtius and Hoffman rearrangement. The very famous reaction involves formation of acyl nitrine from acyl chloride intermediate and its rearrangement to alkyl isocyanate and future transformation of later to primary amine having one less carbon to that of the reactant through hydrolytic cleavage. And you can see the details of the reaction that acyl chlorides when react with sodium azide, how there is a formation of acyl azide, then due to presence of positive charge on nitrogen it will attract the bonded pair electron towards itself. Hence, there is a elimination of nitrogen and on heating we will get the acyl nitrine after elimination of N2. Then there is a rearrangement of R group to the N and the product here is alkyl isocyanate. Alkyl isocyanate on hydrolysis give carbamic acid and ultimately it gives primary amines. So, there is a less carbon. The Hoffman-bromamide reaction accomplishes conversion of a primary amide to primary amine possessing one less carbon atom by treatment with bromine and a base. The details in the reaction you can see that first of all primary amide reacts with sodium hydroxide, then there is a addition of polarized bromine molecule, the formation of N-bromoamide, and there is a rearrangement after acyl nitrene to alkyl isocyanate, which on base hydrolysis further by decarboxylation to give primary amines. Again there is a less carbon to that of the reactant. You can see in the primary amide, reactant is primary amide and the product is amine with less carbon. Dimerization. One of the principal reaction of nitrene is dimerization to diimide. Azobenzenes are often obtained in reactions where aryl nitrenes are implicated. So, you can see in the reaction there is a dimerization of aromatic nitrene. It would thus seem that dimerization is more important for the nitrenes than it is for carbenes, but again it has not been proved that free nitrenes are actually involved or not. At least two types of nitrenium ions, nitrogen analogous of carbocations, can exist as intermediates. Though much less work has been done in this area, and the nitrogen one type is 25 and 26. The 25 is the bonded 2 atoms and in other 26 only 1 atom is there. That is all about the nitrenes. Now we come to the third carbotans we have taken today, free radicals. In any species, what are free radicals? Any species that contains one or more unpaired electron is called free radicals, and we can oftenly say radical. Free radicals are paramagnetic due to the presence of unpaired electron, and they can be detected in ESR measurements. A carbon radical contains an unpaired electron on the carbon atom. An alkyl radical is a tri-coordinated carbon radical bonded to alkyl group or hydrogen atoms. Alkyl radicals are classified as primary, secondary, tertiary according as the carbon having the unpaired electron is bonded to 1, 2, 3 alkyl groups. Structure of alkyl radicals. Alkyl radicals are neutral species in which the trivalent carbon bearing the unpaired electron has 7 electrons in its valence shell. So, nitrenes and carbenes have 6 electrons while free radicals have 7 electrons. 6 of these are 3 bond pair electrons. Evidence indicates that methyl radical has a trigonal planar structure. You can see in the figure methyl radical, and other simple alkyl radical have a near planar shape. Accordingly, the carbon atom having the unpaired electron is in sp2 hybridization state. The 3 sp2 hybrid orbitals form a sigma bond. You can see in the sigma bond with the alkyl group. You can see that carbon with a simple line, with dotted line and dark line with the alkyl group. These are the 3 sp2 hybridized bond, sigma bond with alkyl groups or hydrogen atom which lie in the plane subtending an angle of 120 degree to each other. The unhybridized p orbital is perpendicular to the plane and accommodate the unpaired electron. More highly substituted alkyl radicals such as tertiary butyl radical are flattened pyramidals closer in shape so to that expected for sp2 hybridized carbon than for sp3. The carbon diradicals in which the tri-coordinated carbon is connected. Atoms of high electronegativity such as F3C, when 3 fluorine atom is there, prefer a pyramidal shape. The center carbon is in sp3 2p linear overlap. The unpaired electron accommodate in 4th sp3 orbitals. You can see in the figure trifluoromethyl radical. The pyramidal carbon radicals having 3 different substituents are chiral, but they exist as non-resolvable racemic mixture due to rapid pyramidal inversions of their enantiomeric forms. Non-resolvable, we cannot define whether it is dextro or levo. This is called non-resolvable. Racemic mixture means when there are both kind of enantiomers were there, dextro as well as levo. Relative stability of alkyl radicals. Like the alkyl cations, alkyl radicals are stabilized by the electron releasing effect of the alkyl group. Alkyl group can release electrons either by inductive effect or by hyperconjugation effect. Hyperconjugation involves, what is hyperconjugation? It is the delocalization of sigma orbital of beta CH bond and the singly occupied p orbital of alpha carbon. You can see in the ethyl radical, the beta CH bond and alpha carbon, the greater the number of beta hydrogens, greater will be the hyperconjugation, because we have already stated, we have already discussed that it is the delocalization of sigma orbital of beta hydrogen among beta hydrogen and alpha carbon. So, the increasing order of stability for alkyl radical is tertiary butyl radical will be the more stable, and the then isopropyl radical means 2 degree, then ethyl radical, this is CH2, and then methyl radical, this is CH3. And resonance stabilization of allyl radical. What is allyl radical? CH2, CH, CH2. This is your allyl group. An allyl radical is more stable than a tertiary alkyl radical, even though the former is a primary radical. Why it is? This is because of resonance involving delocalization of pi orbital with the p orbital as shown below. That you can see pi p delocalization in allyl radical, and the two canonical form of allyl radical. So, it is more stable than the tertiary alkyl radical. Resonance stabilization of benzyl radical. What is benzyl radical? When there is a CH2 group at benzene molecule. Benzyl radical is a primary radical, yet it is more stable than a tertiary alkyl radical. Hence, benzyl as well as allyl radicals are more stable because of the delocalization factor. It is slightly more stable than allyl radical. Benzyl radical, like allyl radical, is stabilized by resonance involving a pi p orbital delocalization as shown in the figure. So, you can see the number of resonating structures are there, the stability will be the more the resonance, more will be the stabilization. Stability of other carbon radical. Vinyl radical, ethynyl radical, phenyl radical, trichloromethyl radical, trifluoromethyl radical are less stable than alkyl radicals. On the other hand, radicals next to the carbonyl, nitrile or other functional group are centered on a carbonyl carbon and are more stable. You can see in the figure also that they are more stable, even tertiary alkyl groups, carbonyl group and ether group and aldehydic group, they are more stable than tertiary alkyl radicals. You can see this slide shows the relative stabilities of mostly radicals, that benzyl radical will be the more stable than allyl radical, than tertiary radical. Tertiary will be more than secondary, in which the two alkyl groups are there. It will be more stable than primary, in which one alkyl group is there, and it will be more stable than the methyl radical, which is CH3, and it is more stable than the vinyl radical and phenyl radical. Formation of free radicals. Free radicals are usually generated by hemolytic cleavage of a covalent bond of a molecule or by reaction of a molecule with other free radicals. Homolysis can be affected either thermally or photochemically. The oxygen bond of peroxic compound and carbon nitrogen bonds of azo compounds have low bond dissociation energy. So, these compounds are useful in generating radicals through homolysis. There are the examples of formation of free radicals. That di-tertiary butyl peroxide, when heated at 100 to 130 degrees Celsius, tertiary butoxyl radical will form. When diacetyl peroxide heated at 80 to 100 degrees Celsius. So, you can see in the reaction that is reaction formation of free radicals can form either by photolysis or by thermally. Diacetyl peroxide when heated 80 to 100 degrees Celsius, we will get the acetoxy radical, which will further dissociate it to methyl free radical. Dibenzoyl peroxide when heated to 80 to 100 degrees Celsius, benzoyl oxy radical will form. It will further dissociated to phenyl radical. Azo compounds photochemically or thermally dissociate to give the alkyl free radical. Azo bis isobutyl nitrile when heated to 60 to 100 degrees Celsius, we will get the 1-cyano-1-methyl ethyl radical, which can further dissociated, and chlorine on photochemically gives chloride free radicals. RCOR photochemically gives acyl free radicals. Lead tetraethyl when heated gives ethyl free radical. Toluene when reacts with chloride free radical, we will get the benzyl free radicals. Tertiary butyl hydroperoxide when reacts with cobalt ion, it will give tertiary butyl peroxy radical. Acetic acid when reacts with transition metal, which any transition metal you can take which is in second state generally, gives tertiary butoxyl radical. And anodic oxidation of carboxylate anion will give the carboxylic free radicals. So, there are the reactions in which we can form the free radicals. Reactions of free radicals. In a free radical, the atom bearing the unpaired electron has only 7 electrons, while when we will discuss the carbon there are 6 electrons, but both are electron deficient and its valence shell, so it has a strong tendency to complete its octet by acquiring an electron either through coupling, through disproportionation, a proton abstraction from a molecule, or by reacting with a pi bond. You can see in the slide that there is a coupling of ethyl free radicals, disproportionation between ethyl and product is 1 alkane and 1 alkene, and then there is a abstraction of proton from alkane to form the another alkane. There is a proton abstraction from the one molecule, that this is toluene. Then there is a formation of methane and addition of free radicals to alkenes to give addition reaction. So, these are the reactions of free radicals. So, we have discussed about the carbenes, nitrines and free radicals. These are all are the reaction intermediates. They are generally, it is difficult to find them in a reaction because of their lifetime is very less. So, we have discussed all the intermediates, carbocations, carbanions, carbenes, nitrines and free radicals. Thank you so much.
Thank you, ma'am. Thank you so very much. I hope that all the students who might have watched us with the help of this lecture would be able to understand what basically carbines, nitrines are, because though we have time left over here, so if we want to summarize the carbines or the nitrines, what would we say about these terms?
Okay. We can summarize it that carbenes are the as carbenes and nitrines both are exist in singlet and triplet state, both are electron deficient, both can be identified, just like carbenes can exist as singlet as well as in triplet state. But how can we identify that a particular carbene is singlet or triplet in a particular reaction? It is given by Scales process. Then when a singlet carbene reacts with a cis compound like cis pent-2-ene we have discussed in our slides, it will give the same product. It will react stereospecifically and stereochemically. Stereospecifically and stereospecifically it reacts. How it, when a cis reactant combine with singlet carbene, the product will be cis. This is called the stereospecifically reaction. But when triplet carbene is react with any compound like cis pent-2-ene or trans pent-2-ene, the product is a mixture of the product like cis as well as the trans. Why it happens? Because we have already said that in singlet carbene there is the electrons are the spin of the electrons are opposite. So, they can easily form a bond but in triplet state the spin of the electrons are paired. So both electrons cannot form a bond simultaneously, they will form a bond one after the another. When first of all one electron formed a bond, then there is a possibility of rotation of single bond, because we are adding the to the alkenes. Then when one electron can form a bond, that there is a free rotation of carbon carbon bond, and there is a energy then there is a formation of another product. So this is the basic concept when singlet and the difference between singlet and triplet carbene. Same thing we are observing in case of nitrines also. But when we are talking about free radicals, in free radicals there are only 7 electrons. In carbenes and nitrines there are 6 electrons, they are electron deficient, they want to stabilize themselves, that's why they are highly reactive. In fact, it is very difficult to isolate the singlet carbene or triplet carbene. Actually the singlet carbene is formed, but it is then converted to triplet carbene. The energy difference is very less between singlet carbene and triplet carbene. So in free radicals there are 7 electrons, they are also electron deficient, but the because there are 7 electrons, and in carbene nitrine there are 6 electrons, carbene and nitrines are highly reactive molecules. As we have discussed about in the carbocation and carbene ions, same in the free radicals, there is a effect of inductive effect, there is a effect of hyperconjugation effect. More the alkyl group, more will be the resonance, more will be the delocalization, more will be the stability of intermediate. So we can say that when there is a 3 alkyl group attached to the free radical will be the more stable, and tertiary alkyl radical will be less stable than benzyl and allyl because of the delocalization of electrons, because of hyperconjugation. So these are the points we can say that these are the intermediates. So with this I can say that we have discussed all the intermediates which are generally formed in the reactions.
Because we are carrying a series and under this series we studied a lot, and today we studied about the carbenes and nitrines as well as the free radicals. So what else we have left in this particular series further?
Actually we have discussed all the intermediates. In the further series we will discuss the functional groups like aldehyde, ketones, esters. We can discuss also the cycloaddition reaction, the concerted reaction we can also discuss. So now we will come to the functional groups: aldehyde, ketones, esters, their derivatives, and number of functional groups.
Definitely we would be coming again with this particular series, and we would be discussing all what Dr. Vandana has said. And I would like to tell you all that if you want to access this particular lecture, you can definitely access this lecture, as we daily upload our lectures on the YouTube, with the help of which you can study your course material. Thank you, ma'am. Thank you so very much for giving such a nice lecture, and we would be again for you with another lecture in the series. Thank you.